Hi, today I want to talk about quantifiers. So quantifiers are these silly looking symbols that you may have seen in a past course, right? So the upside down A, the backwards E, sometimes you'll see these in calculus in the context of maybe a delta epsilon or an epsilon definition of a limit. These are the quantifiers that we use most typically in mathematics. And what these are, honestly, are just shorthands. So the upside down A is a short way of writing for all, or so, sometimes people say for every, but you can think of it as A for all, right? And then the backwards E is an existential quantifier. So you can think of it as a backwards E for the word exists, right? So these are the two main quantifiers. And what they do is they let you define statements that have variables in them, right? So typically what you do is you write a quantifier followed by a variable, followed by some statement involving that variable. And if you do that, now you have a quantified statement that is known as a predicate. So that's we're sort of expanding our system of logic, right? And previously we had talked about what is known as propositional logic. And propositional logic is if you just have P, Q, R, and you have implies and or and not and so on, right? That is the language of propositional logic. And here we're tossing in these quantifiers to extend our language of symbolic logic out to what's called predicate logic. So it's a bigger language. There are more statements in the land of predicate logic. So I want to show how this works a little bit in some examples. So where one place, a really nice place actually where quantifiers come up often is in definitions. They're very, very, very useful for defining ideas. So here is an example of a definition that would involve a quantifier. Suppose we want to define what it means for a number to be even, a concept we're super familiar with, right? So you could say a natural number n is even, right? If and only if it can be expressed as twice another natural number. Now, there I just wrote it out in words, but let me write it out, the same idea using quantifiers. Right? So I can say that is if and only if there exists an m in the natural numbers such that n equals 2 times m. Okay. So this right here, this would be an example of a quantified statement, right? It's an existential statement. And once again, as I said it out loud, but I want to write how I read it, how you speak a statement like that. So what I just said is there exists, that's the backwards E. There exists a natural number m, right? That's the little euro symbol, and then the n with the extra spine, right, is saying in the natural numbers, in the an element of the set of natural numbers, right? Now, in that quantified statement, I didn't literally write the word such that, but after you do an existential, basically when you see the comma, you always say such that. It just reads a lot more naturally, right? If you say there exists m in the naturals, n equals 2 times m, right? It just sounds sort of robotic. So to make it, even though it's not always written in mathematics, anytime you speak it, you always say such that after you say there exists quantification, right? So there exists m in the naturals such that, right, the comma, you kind of pause, say such that, and now we say what the condition is, such that n equals 2 times m. So that would be an example of a the kind of definition that would use a quantifier, right? Now, this is a a perfectly good quantified statement with an existential quantifier. What I want to do now is I want to think about what the opposite of this statement would be, right? I want to think about what would not even be, right? Let's construct the negation of this statement, just as an exercise. Let's define not even, right? Using the negation of our statement above, of our property above. So here's what I want to do. I want to say a natural number n is not even, right? Let's figure out what this definition must be. In fact, we have a special word for not even, odd, right? So you can call it not even, or you can call it odd, whichever one you want to call it, right? The concept of not even comes up frequently enough that it has a special name. So, a natural number is not even, or if you want to say odd, right? If and only if what? Well, if you want, you could say if and only if it is not the case that there exists m in the natural numbers such that n equals 2 times n. So, okay, in symbolic logic, that was pretty easy. All I did was slap a not in front of the statement, and now I've defined odd. I've defined not even, right? But that's maybe a little bit unsatisfying because it doesn't feel like we did much, right? We just said, okay, well, even means there exists a natural number such that n is 2 times that natural number. And so not even means it is not the case that there exists a natural number such that n is 2 times that natural number, right? Or 2 times this other natural number, right? It doesn't feel like we really did anything. Well, and it also feels a little bit unnatural, a little bit robotic, right? It's a bit like the Borat scene where he's trying to, say this jacket is black, not right. Right, you just sort of slapping a not at the end of a statement or at the beginning of a statement and not somehow incorporating it into the statement maybe feels a little bit unnatural. And so how could we make this statement a little bit more natural sounding? Here's what you can do. Think about if it is not the case that there exists an m such that n equals 2 times m. What must be true? What must be true is it must be true that for every single natural number, m, if you checked and asked, is 2 times m equal to n? The answer will be no. Right? If it's not the case that there exists even a single natural number whose double is n, then it must be the case that if you ran through all of them, right? That's why I changed it to for every. If you ran through all of them and you checked twice that quantity, you will never see n, right? It will never be equal to n. That must be what it means to be odd, or at least one characterization of what it could mean to be odd, right? So here, what we have is we have another way to say this, right? You could say that odd, right, means what? It means that for every natural number m, right, and is not equal to 2 times that n, right? So what essentially happened here, if you look at what happened, is we had a not out here. And what we did was we moved the not inside the statement. But when we moved the not inside the statement, what was the price we paid? We had to change the quantifier, right? We had to flip the existential quantifier to a universal quantifier, right? The there exists becomes a for all, right? And this is, once again, this is something that works outside the domain of mathematics. Also, if you're just talking about sort of English language statements, say I told you there does not exist a cat that is purple, right? Then what could you say? Well, you could say that means that for every cat in the world, if you check the color on that cat is not purple, right? There does not exist a purple cat is equivalent to all cats are not purple. They're the same claim, right? Exactly the same claim. And so here we saw it in the context of mathematics, but even an odd, right? But you can also talk about cats being purple, and it works just the same. This is actually a very common property of used in logic, in predicate logic, a very important property called De Morgan's law. Right. And De Morgan's law says that exactly what we did is valid. That if you have there exists x such that p of x, right? If you have some statement p that takes a variable x, and you say it is not true that there exists an x such that p of x, that is absolutely equivalent in every way to saying that for every x, not p of x. So that's De Morgan's law. You can move the not inside and change the quantifier. It turns out you can also do it if you're starting with a negation of a universal quantifier. It works the same way. If you want to move the negative inside, you can do that for the price of changing the quantifier, right? You can change the for all to a there exists as you move it inside. Right? So this is De Morgan's law. So, we saw the first part of De Morgan's law. We saw this used up here, right? The second version you may have seen before, but maybe just slightly disguised, right? This is a property of logic that comes up very, very, very frequently in mathematics. This is whenever you're tasked with finding a counterexample, right? That's actually it's disguised a little bit, maybe, right? But that's exactly what's going on this second line with De Morgan's law. So here's an example. Let me make it concrete with, say, a common example from calculus. So here's an example in say the domain of calculus, right? So suppose someone says to you, maybe your calculus teacher said something like this to you at one point in time. So how about prove or disprove that that f is continuous whenever the absolute value of f is continuous. Right? Suppose someone says that to you. So what really is going on here if we translate this into the domain of predicate logic, right? Here's really what we have is we have P of F being the statement F is a continuous function. That's the statement that we're considering here. And we want that to be not just that f itself is continuous, but we want that f is continuous if absolute value of f is continuous, right? This is the claim that we're looking for, right? And if you want, you can actually make it even a little bit more symbolic logic. If you want to, you could write it with implication, right? So you could write it like this. You could say that P of f is the claim that absolute value of f is continuous, implies f is continuous. So then what could we do here? When we say prove or disprove this, what do we mean? We mean prove this as or disprove. Is this true for all f, right? That's what's really being asked here. And it's sometimes a little hard to say it very precisely back in Calc 1, because you haven't talked about things like quantifiers, but that's really what's being asked. We're saying, is this always true? Can you always conclude? Always, for all functions f, right? We tend to decorate our sentences with words like always that or indicate quantifiers, right? So we're saying, can you always conclude for all functions f that just because absolute value of f was continuous, then f itself must necessarily be continuous, right? So what we're really asking here is we're saying, is it true that for all f, right, for all functions f, f is continuous, implies, sorry, absolute value of f is continuous, implies f is continuous. All right, that's what we're asking, right? So I'm going to claim it's not. I'm going to claim that this is not correct. It's not true that for all f, absolute value of f is continuous implies that f is continuous. And how will I demonstrate this? I'm going to disprove this via counterexample. And specifically, here's what I'm going to do. I'm going to just construct one. I'm going to construct this function. I'm going to construct the sine function of x, right? And when I mean sine, S-I-G-N, not S-I-N-E, right? What I mean is it's just a function that's 1 if x is positive, and I'm going to actually say greater than or equal to 0, right? You have to decide where to put that endpoint, and it's -1 if x is less than 0. So I'm going to lump 0 in with the positives. So it's a slight tweak on how sine is sometimes defined. Sometimes 0 is its own case. But basically, just strip off the sign of x, right? Call it 1, +1, right, if x was a positive number, and call it -1 if x was a negative number. So consider, oh, the pod is cooling down. I need to make a fresh one. What are we going to do here as far as this graph, right? We're saying it's the function whose graph looks like this. It's +1 if x is already positive, and it's -1 if x was negative. And like I said, 0, I'm just throwing in with the positives. I'm choosing to, right? So I'm going to define this function. Well, if I look at this function, what do I have? I have the absolute value of this function would be what? Well, the absolute value of this function would be identical over here, right? But it would, On the left-hand side, it would flip up to positive 1. So the absolute value is actually just the constant function 1. Right? And constant functions are continuous, right? So we could say then, what did we just find? So I found that f, for this particular f, I constructed one that this f is continuous, right? But f without absolute value, so f in absolute value is continuous, but f without the absolute value is not continuous. So what did, now think about how an implication works, right? I have a true and a false, right? True implies false is false, right? So what could you say? You could say, thus it is not true that f is continuous implies f is continuous, right? If that, just because the absolute value, so it's not the case for this particular function, this specific f, right? It's not true that f is continuous. Absolute value of f is continuous implies f is continuous, right? So what you could say is, we just found that there exists an f, in particular, the sine function. We constructed one. There exists one, because look, I just built it, right? So this is why with the counterexample, you want to be very specific because you're constructing an example. So I can say now there exists one because we constructed one. So there exists an f such that it was not true that f is continuous implies absolute f is continuous implies f is continuous, right? That was not the case. De Morgan's law, right? Look at what I said up here. I said that this property is exactly what you do when you find a counterexample to a proposed identity, right? This is exactly what we're doing. We have, there exists something such that not something. So what can I do with the not? I can pull the not out of the quantifier, right? It ends up out here, as long as I flip the quantifier. So that's what I'm going to do, right? Factor the not out of the statement, and the statement becomes not for all f. F is continuous implies f is, absolute f is continuous implies f is continuous, right? So it is not true that for all functions f is absolute value f is continuous implies f is continuous, right? Because I found a specific one for which it was not true, right? So this would be called proof by counterexample, right? I just disproved this statement, right? This statement that this claim, this proposal that f is continuous whenever absolute value of f is continuous, right? This would be a disproof of that by, and essentially you're using De Morgan's law here, right? You may have seen arguments like this in past courses. You probably didn't frame it in terms of De Morgan's law, but it was there behind the scenes the whole time, right? So, so this is a right on this step, right? We used De Morgan's law, and we showed that it is not the case that for all functions f, the absolute value of f being continuous implies f is continuous. So, and we're done, right? We successfully disproved that by constructing a counterexample. All right, so there's a little introduction to quantifiers. They make the mathematical language a lot more complicated, as you can see. Most mathematical ideas require some quantifier to express, right? Even something as simple as evenness, as you've seen. So great, thanks. See you next time.